Then today we have Fabrizio from Imperial College London and Christian from Cambridge University presenting the Weisfeiler and Lehman Go Cellular paper, CW networks. Yeah, and they wrote it with Nina Otter, like you can read the names, I guess, but Nina Otter, Yu Guang Wang, Pietro Liu, Guido Montufar, and Michael Bronstein. I'm hoping I'm pronouncing some names right. And yeah, hi Fabrizio, hi Chris. Do you want to tell us about CW networks and CW complexes for graph neural networks?
Sure. Thanks for having us. So as Hannes mentioned, we're gonna present our latest paper, which you can find at this archive link in the corner. Some elements of it will be based on this previous work we've done, and that's the second archive identifier. There's no need to be familiar with that, but we might refer to it from time to time. So just so you know where to find that. Okay, let's get started then.
Well, before we start, let me make the usual interruption that please feel free to speak up at any point and ask questions. Unmute and ask questions. Yeah.
Yeah, definitely. Feel free to ask and interrupt. Right. So let's first understand some of the limitations of graph neural networks that kind of led to this work. And perhaps the way you should think about these limitations as you see them being mentioned is as in graphs are not enough. Probably that's one of the main themes here. We need spaces with more extra features to do more interesting things. So the first limitation I want to mention is group-wise interactions, or sometimes called high-order interactions. So sometimes you want to say some entities, they interact as a group together at the same time. And that's not possible with graphs because they, by definition, they describe pairwise interactions. So that's a problem. Another problem is about high order structures. So graph neural networks sometimes can't detect certain high order structure, as in this example here. So for instance, these triangles are not identified by common graph neural networks, and they believe these graphs are identical. And it's not only about identifying them, but also about like explicitly modeling these sort of structures if they are relevant for the problem, not just finding them, but actually explicitly taking them into account. Another problem is high order signals. So again, this is related to the previous two problems, but if you have some sort of high order objects, these might also have some features. So how do you process those? So a classic example here is with edge signals. Edges are often treated as some sort of byproduct in graph neural networks. They're kind of there just to link nodes, but you know what happens if you have only features on the edges? What should you do with them, and so on. Then another problem that has received lots of attention lately is about expressive power. So classic message passing graph neural networks are as powerful as the WL test, and many things have been proposed recently. And one big question here is, you know, like, can we also design other hierarchies parallel to the WL hierarchy, and generally more expressive architectures? And finally, something that you will see mentioned quite often are long-range interactions. So something that's a bit annoying in graph neural networks is that you have to chain a lot of layers to actually get interactions between nodes that are far apart. And you know, when you chain lots of layers in graph neural networks, currently you have all sorts of problems like oversmoothing and so on that have been studied in the literature lately. All right, so if we want to choose another space or like something more complicated than a graph to do our job, what should that be? And what we look at in this paper are what's called cell complexes or CW complexes. We use these terms interchangeably. Sometimes you might see some slightly different definitions between these. But I think it's most useful to just look at an example rather than see definitions here. So we start with some vertex set, which is finite. So this is something you see in graphs as well, just a bunch of points. And now the first thing we do, we take some strings and we attach the boundaries of the strings. So the endpoints, we attach them to some vertices we have already here. So let's choose some strings and attach them to these points, and we get something like this, which, surprise, surprise, looks like a graph. This is important. Any graph is a cell complex. So cell complexes are a generalization of graphs. And that's something good to keep in mind. Now, something we can do here further is to generalize this procedure. So if you think what we did, we took like a one-dimensional thing, a string, we found its boundary and attach it to some things that were already present. Now we can kind of do the same thing, but in the next dimension. So instead of taking a one-dimensional thing, we can take a two-dimensional thing. So that would be some sort of surface and attach its boundary in a nice way to what we already have. So that surface could be like a closed disk. We take its boundary, so that's this dark contour you see for these two, and then we can attach it homomorphically. So that's just saying gluing it nicely to some simple cycles in the graph. And once we finish this gluing, so this just shows how you would identify these things. And now once we glue them, it kind of looks like this. So you should imagine this maybe as kind of two drums connected by a string or something like that. This is what we call a two-dimensional cell complex. And what all these elements are called cells. So the vertices are 0 cells, the edges are 1 cells, and these things we've just added, these blue shaded objects, they are called 2 cells. Something important to notice is that if these gluing procedures are nice, then we can define a partial order for these cells. So if we label the cells using Greek letters, then we can say that tau is less than sigma if cell tau is on the boundary of cell sigma. So you can see some things are on the boundary of other things. So for instance, some vertices are on the boundary of these disks we've attached, these 2 cells, the edges are on, some edges are on the boundary and so on. So we have this partial order. And the nice thing is if the gluings are nice, then this partial order completely describes the topology of these surface you see here, or well, not necessarily surface, but like this space. So we can kind of disregard this geometric picture you have in front of you and just think of it in terms of this abstract partial order. And then we can use it to define adjacencies. So let's see how we might do that. So we can define adjacencies, and with these adjacencies, we can generalize the color refinement perspective algorithm you might be familiar with from graphs. So here we just have like some cell complex you see here in this example, and each cell, so each edge, each vertex, and this 2 cell, this rectangle you see here, each has a unique color. We just assigned unique colors to aid the visualization. They might have some general colors, and we want to kind of do some color refinement. So the way to do that here is shown for this yellow edge. So we take the old edge color. So this is very similar to like WL, where you use the color, the previous color of the node. Then you have the first type of adjacency. So you look at the boundary vertices. So these are colors of the vertices on the boundary of this yellow edge. So this purple and dark navy blue colors. Then you look at any cells this edge might be part of. So it's part of a single 2 cell, this red one, and we put its color there in this hashing function. Then there are other edges that are part of the same cell. So there are other 3 edges that are part of this cell. And we also include the color of the shared cell. Something important to note is here that this kind of implicitly aggregates long-range information. So for instance, the light green edge and the yellow edge, let's see if I can annotate this thing. So this one and this one, well, they're kind of, well, they're not strictly close in the graph, but like if you think in the cell complex, they are closer in some sense because they are part of this common structure. So we kind of aggregate, when we consider this light green edge here, we aggregate long range information. All right. Then we have also the line graph adjacencies kind of thing. So if 2 edges intersect in a common vertex, then they are adjacent. And we also include the color of the vertex between them. Right. Something we've shown that's important here to state is that we can kind of get rid of 2 of these. and you don't lose your ability to distinguish cell complexes. So you're going to be as powerful if you remove these two. And that has some important consequences for computational complexity. And this generalizes all the results from the other paper I mentioned. But we're not going to go into that. Okay. Actually,
okay. Can I interrupt and go back to that slide?
Sure. 1 second. Just,
so if
okay.
we have a 2D graph,
yeah.
Oh, no, a 1D complex only. We're only looking at 1D complexes or cells.
Mm-hmm.
Yeah, 1D cells, I think. And we only look at the second type of aggregation that is not grayed out right now. Then we would have the
yeah, okay.
Then we would have the usual double WL test, right? Like if we only look at upper adjacents.
Yeah. So yeah, then no edge is upper adjacent to any other edge because, well, there's no high order structure to kind of make them adjacent in some sense.
Yeah, but the nodes are upper adjacent, and then we pass the colors between the nodes and have the usual WL test.
Yeah, exactly.
Okay.
Yeah. So assuming all the edge colors are kind of the same all the time, you kind of get you get kind of the same thing. Yeah, that's a good question. Okay. Now, something you asked is, like, I never seen a cell complex data set. So, what is this useful for? So we always work with graphs just because, well, it's easier to record sort of dyadic interactions between things. And then what we have to come up with is a way to kind of transform graphs into these higher dimensional cell complexes that might help us solve some task. So we already saw such a procedure by just gluing these higher dimensional cells. So that's one example based here on cycles. So you just glue these two cells wherever you see like a simple cycle in the graph or an induced cycle. So that might vary depending on what you prefer. Another example that we examined in our previous work was based on cliques. So each clique in the graph on the left produces what's called a simplex on the right. So you have this kind of filled triangle on the right and a tetrahedron. So you should imagine this tetrahedron as an actual solid surface with stuff inside it. And that's also like a good example of a three-dimensional cell, but generally we're going to stay in 2D. And both of these are example what's called a skeleton preserving lifting maps. So what we mean by that is that you can kind of imagine these graphs as some sort of scaffold you put things on top. And as long as you don't change the scaffold, so as long as you don't add any new edges or new nodes, then you get something what we call a skeleton preserving lifting map. And they have a nice property. So if you lift graphs in this way, like in these two examples, for instance, then you're going to be at least as powerful as the WL test in distinguishing these input graphs. So this is a nice property. Now we also have like some stronger results. So here's one of these results. So for this hyperparameter K, which essentially specifies the maximum size of this substructure, so be it cliques, cycles. So when this K is at least 3, we can show that CWL with multiple lifting maps is more powerful than WL. So these maps are either the clique complex lifting you saw on the previous slide with cliques of size at most K, the map that attaches 2 cells to the simple cycles, and the one that attaches 2 cells to induced cycles, or the union of these. And maybe it's useful to look at some examples. So these are 2 pair of graphs, neither of which can be distinguished by the WL test. And what you see here are the colorings of WL, just to see they produce the same histograms. And one of my main points here would be that what sort of lifting map you use might depend on the application. So cliques are very common in social networks, but they're not so present in molecules. So for instance, the clique complex lifting would not help you at all to distinguish the 2 graphs on the right because there are no cliques there. But an induced cycle-based lifting would definitely allow you because you have induced cycles of different sizes, and CWL will, it can be shown, it will immediately recognize they are of different sizes. So again, like it depends on the application, and by no means is not a complete list. Like you can have something like, I don't know, if you like pyramids or something, and pyramids are essential for your task, you can kind of glue some cells that kind of take the shape of a pyramid. And that could be like some sort of motif that will modulate your message passing. So this is not a complete list of lifting transformations. And finally, the same lifting transformations I've mentioned in this result, you can also show that CWL is not less powerful than 3WL. So what that means, there is something that 3WL fails to distinguish, but this CWL procedure will distinguish them when you use these liftings. And this is for some values of K that are specified here. All right, I think that's all from me. So I'm gonna hand over to Fabrizio.
Thanks, Chris.
Well,
maybe if there are any questions at this kind of break.
Yeah. What is that? What is it? I guess what is it that a CWL test can do that a k-dimensional GNN cannot? Do you know? Well, Surija is raising his hand. I guess you can ask yourself.
Right. So like for KW.
Do you want to unmute yourself to explain what you mean with k-dimensional GNN? Maybe? Okay, no, then Christian, Fabrizio, do you know what k-dimensional GNN means anyways, and can answer this question?
Yeah, so I guess you can answer this at multiple levels. So there are these like algorithms that kind of work. I suppose it's referring to these algorithms that they lift graphs into these higher dimensional tensors, and then you apply these linear equivariant maps plus non-linearities. So they have been kind of shown, or there are also these folklore, WL, GNNs, and so on. So we have some results in lower dimensions. So I guess this theorem 15 here is one example where obviously a 3WL GNN, which is as powerful as 3WL, will not be able to distinguish the pair that this theorem is mentioning, but CWL and also the message passing procedures you're going to see soon will be able to. Another thing is that with these tensors, they get very high dimensional very quick. So if you explicitly want to mention some structures that are quite large, so imagine like a 6 ring, which is very common in molecular applications, well, you need the tensor, which is number of nodes to the power of 6, which becomes kind of, like it's too much memory wise, and these are dense tensors. And you can't explicitly model these structures, even though you might recognize them implicitly, but you don't explicitly model them. Hope that answers at least partially. Maybe we can chat more about it afterwards if it's still not clarified. Any other questions or?
I guess not. Let's go.
Right.
Cool. Okay, so I will continue with the talk. We'll go now through a more practical implementation side, maybe, but still very important for applications. It is how do we define an actual neural model that can implement the WL test we've just described. And well, the idea is very simple, and we basically borrow it from what has been already explored in the Gene paper. And by the way, we will talk about this in terms of molecular message passing, simply to ground the discussion, because it's very easy to imagine, as we've already had these examples on basically molecular-like graphs. It's very easy to imagine to have basically nodes as 0 cells, edges as one-dimensional cells, and then we can consider, for example, rings or induced cycles as 2-dimensional cells. And this is probably one of the best way to model molecules with cellular complexes, and we'll talk about this now. So again, we consider only dimensions 0, 1, and 2. They correspond to nodes, edges, and induced rings that are glued to that gets glued with basically closed two-dimensional disks. And yes, so the idea is that when we want to embed an entire complex, we perform this readout operation on the multiset of representations of these cells at the last layer. These are how do we get this? Well, again, we have several layers. At each layer, we update the representation of a cell at any dimension as a function of its current representation and messages. So we have two messages. One comes from boundaries and one from the upper adjacent cells. And we describe them here. So the message for upper adjacent cells, for example, they are simply aggregated via a message function, which is a function of the representation, the current representation of the cell we are updating, and the neighbor, in this case tau, and the representation of the shared co-boundary, which in this case is represented as delta. We have also, on the right, you can find this cartoon that explains what happens, where basically the color of each arrow corresponds to a different kind of message that is exchanged. Right, so what we, this is basically, of course, one of the most natural way to define a neural network that can implement the WL test, the cellular WL test we described. In the paper, we showed that this model can be at most as powerful as CWL. And the way it achieves the same expressive power is by using basically parametric aggregators that can be learned to be injective, pretty much as it happens in Gene. So we now have basically an architecture parameterized this way that for which we have some theoretical guarantees. That is that we can potentially achieve the same expressive power of the WL test on cellular complexes that we defined. So a few advantages of this network are, well, of course, the first of all, we have that we now model long-range interactions. So, for example, in molecular modeling, we know that this is sometimes we have molecules whose properties depend on the property of nodes at opposite sides of rings, for example. And as Chris already illustrated with the cartoon, when we apply CWL and also in this case CWNs, we kind of create shortcuts between nodes when they are, in principle, we create shortcuts between edges when they are in the boundaries of the same two-dimensional cell. But in turn, this will mean that transitively we create shortcuts between nodes. And yes, and it means that we need a smaller number of layers to basically allow the information from one node to propagate to another node if we have rings in between intuitively. The second advantage is that, well, of course, the expressive power. So since we know that we can match the expressive power of the theoretical test, then there are basically molecules which in practice we can distinguish, and the WL would not be able to distinguish them, so therefore not even standard GNNs. And of course, the other side of this statement is that we are able to capture and make proper use of substructures, for example, aromatic rings. And this is more or less what we mean also by higher order modeling. It's not just the fact that you are able to it's not just that the network is aware of the presence of these substructures, but it's also that they are actually properly modeled. And at the end, you obtain a representation for each of these higher level cells. So for example, edges and rings in this case. And they have representation which is updated at each layer, pretty much as we do with nodes in standard GNNs. Okay, so what about complexity, right? Because of course there's always this trade-off between computational complexity and the expressive power of the algorithm. So if you want to quantify it, well, we can consider that for a cell at a certain dimension, say for example P, a cell dimension P, we can quantify the number of boundary messages, so messages which are exchanged, so which gets to such cell from the boundaries. And if we consider the cell as a certain cardinality of its boundary, for example, K, well, this is exactly K. But let's say that we can upper bound the maximum boundary size with a number which is, say, a figure which is, say, BP. So the number of boundary messages is basically BP times the number of P cells, or at least this is an upper bound for it. At the same time, we can also quantify the number of upper messages which are exchanged basically at the level below, because this P cell induces adjacencies between the boundaries. And yeah, it turns out that we can quantify it this way with this formula I highlighted here, and we have an overall estimation of an upper bound for the complexity, which doesn't look pretty nice, but in turn, if we consider the fact that BP and SP, which is the number of P cells at a certain level, if we consider them to be also, if we consider the maximum dimension of the cell complex D to be fixed and constant in practice, and we consider them to be also small constants, which is the case in practice when we model molecules, well, at the end, we can rewrite this equation and we get something which is linear in the size, on the overall size of the cell complex. In practice, we observe, for example, that at inference time, our model compares pretty well against, for example, Gene, in the sense that Gene is only from 20 to 35% faster than our model on Zinc, which is one of our benchmarks. So in practice, it's definitely fine, especially if we want to model molecules, and thanks to the fact that we can discard some of the adjacencies. So of course, we also have to consider the complexity of the lifting procedure, not only the message passing. And well, of course, in general, this might be quite computationally expensive, but in practice, when we work with specific substructures of a certain maximum size k, and on graphs in which their distribution is such that the cell complex will inherit some form of sparsity, such as in the case of molecules, then we get very good empirical timings. So here we just reported some numbers. If we also parallelize the lifting approach, because of course it's embarrassingly parallel with respect to the number of independent graphs in a data set, then we simply need around, for example, I guess 1 minute to lift the all-mole HIV graph, considering lifting procedure with a very general lifting algorithm. Of course, you can also use specific lifting algorithm, substructure, isomorphism algorithms. For example, we have algorithm specific that are optimized for rings. Yes, so in principle, again, in theory, it might be quite computationally expensive. In practice, it works very well, especially in the case of sparse cell complexes. Just maybe let's take a look to some synthetic results on synthetic experiments. We first experimented on a benchmark called the circular skip link dataset. So this is a benchmark for expressive power. Yeah, so the data set is made up of graphs which are 4 regular graphs, and they cannot provably be distinguished by the WL test, and therefore this explains why standard message passing neural networks attain basically the same performance of a random guess. Whereas if we use a method which is probably more expressive, then we can actually disambiguate between all possible pairs. And this is what happens in practice with our model. We are able to distinguish all possible isomorphism classes in this data set by using a ring lifting procedure. We do have also another benchmark which is very similar, but it's slightly different in the sense that the graphs that are contained in the data set, they are strongly regular graphs. So they're even more difficult, so to say, to disambiguate. So the 3WL test, for example, cannot distinguish them. And we show that if we have our SIM architecture with basically ring lifting, as soon as we introduce ring lifting up to size 5, so we consider rings up to length 5 to be size 5 to be 2-dimensional cells, then we can basically distinguish all possible pairs. And of course, we think that, well, if you use this somehow, what you already do in the preprocessing step, which is the lifting procedure, might already be enough to distinguish these graphs. So we implemented a very strong baseline that is an MLP with some readout ran on the basically on the substructure count, so on the number of induced rings that we would find with the lifting procedure. And this baseline is very strong and attains very good performance, but at the same time, we notice that we always get something. We always gain something by performing message passing with our network with respect to this basic baseline, which does not. So this is again something reassuring. We also have another synthetic benchmark, which is called the ring transfer. So the idea was to prove in practice what we hypothesize would happen in theory. That is, that we can actually model in a proper way, capture in a proper way long-range interactions between nodes. So the idea is that we create these synthetic benchmarks in which each graph is simply a ring. And we have two special nodes. One is called source, one is called target. We want to output an embedding for target which matches the features we assign to the source node. So to some extent, we want to transfer the information we have in the source to target. And this is a control scenario, just to appreciate what to understand whether our sim model with a constant number of layers as we hypothesized, in this case 3, will be able to solve this task. And indeed, this happens. So even if we increase the ring size up to 30 nodes, with, again, a constant number of layers, which is 3, we are able to optimize a network, the parameters of the network, to learn an efficient message passing scheme to transfer this information across the ring. And this is instead not what happens with the standard GNNs. We just experimented with GN, and we verified that, first of all, when you use a number of layers which is smaller than half of the size of the ring, we basically always get random guess performance, because of course we are not able to propagate the information in any way. So the only hope we have is to have at least a number of layers which scales linearly with the size of the rings. In this case, we have for each ring size network with basically the same number of layers which is half of the size of the ring. And in this case, well, up to rings of size 22, we are able to more or less solve the task. But after 24, like from 24 onwards, basically we are not able to optimize, to train the model to solve this task anymore. So the performance get to the random guess again. And this verifies the fact that in principle, the network might be able to solve this task with such a large amount of layers, but in practice, this is not going to happen. Okay, let's get to real world examples. So this is a classic. Hannes, yes.
Can I go back to the static test here that we're doing? So the network that's having the problem is GN, and if we're reaching 24 layers, we get the problem with GN, but with CIN, CIN,
yes.
if we choose the size of the cycles that we live large enough, then we are able to solve it in a constant number of steps.
Yes.
Okay, and
okay. So intuitively, maybe. So what happens is that you kind of have to learn to propagate the information from one node to an edge, then from the edge to another edge with the upper adjacencies, which are induced by the presence of the two cells, and then back from the edge to the node. This would allow you to solve the task. And you can do this with 3 layers, basically.
Well, okay, I thought we would only have to, why is it 3 and not 2? Because in the first message passing step, we get the information from our node to our bond. And then in the second, because our bonds are connected, in the third, our bonds are connected by a phase. So we pass between the two bonds that are distant. And then I guess the third one is needed to get it from the bond to the second vertex.
Yeah, that's precisely the case. Okay. The thing is, we always read out at the level of nodes. So we don't, at the readout phase, we don't have access to edge space. Yeah, and the way this information gets from edges to nodes is by in this case is by means of the if you remember in the cartoon we have or in the message passing equation we have also the that in the upper messages we have the representation of the shared co-boundary. So in this case basically if we have thanks Chris. So in this case yes, it's basically this delta here. So in this case, two nodes they would be upper adjacent because they share, for example, they are part of the same edge. So if that is the edge where the information has been transferred to, then when message passing happens between these two nodes, then you also get the features from the edge. And so this would effectively transfer the information from the edge to the target node.
Yeah, that's also something I wanted to ask because for the CWL test, right, we said that we can drop the co-boundary and we only need the upper adjacency and the boundary to be as to choose our coloring to be more powerful than the WL test or to be as powerful as CWL if we were to use everything. But now in your message passing, you also use the co-boundary, right, to get information from edges to nodes and from faces to bonds.
Right. So the message passing we implemented for that specific test benchmark is the one we showed. So the one in which we drop the co-boundary and the lower adjacent inputs in the update step. So, but still, nonetheless, we are able to transfer the information from edges to nodes simply because we include the feature of edges in the message between nodes, in the messages between nodes, upper adjacent nodes. So here it will be the counterpart of this here would be the fact that we have the red. Yes, thanks, Chris. So the red color that is included in the messages between upper adjacent edges. It's the same.
Okay, but if we don't have the co-boundary, then we don't get the information to the nodes, right? Like our nodes never get information from something higher up.
I mean, it gets it not directly, but implicitly, thanks to the fact that we include explicitly this information in the messages between upper adjacent nodes. It's basically what you do with the, for example, any GNN in which you also model edge features. So if, for example, in the GNE layers, when you use edge features as well, in that case, well, the messages are always between nodes, right? So you don't have anything which is higher than nodes in standard GNNs, but the fact that you include specifically edge features in the messages, you somehow propagate, you can think of it, information from a higher dimension back to the dimension of nodes, which is 0. So it's the same principle. You just augment your messages with the features of something which is higher, which in the case of GNNs might be edges. In the case of a CWN, maybe either edges or two cells. Yeah.
Okay, can we go back to the message passing slide?
Yep.
1 second.
So just to be sure, in every case you use all, in every case you use the boundary, the co-boundary, and the upper adjacent neighbors to construct these messages.
Yeah. So we have two kind of messages. So one is the boundary one.
Yes.
Okay.
We have two kinds of messages, but in every CW network that you try on the different benchmarks, you always have these two kinds of messages that use both the boundaries, the upper adjacent and the co-boundary.
Yes, yes. This is the same architecture we use for all benchmarks.
So I think the confusion might be from the fact that there is some overlap of information between some adjacencies, and that's why we also able to remove some of them. So some of basically the co-boundary information also shows up in the second entry of the tuples in upper adjacencies, if that makes sense. So basically,
yes,
like in
yeah.
I mean, that's also the reason why we were able to drop them without losing expressive power, because we don't lose the information. We still have them. It's just that they are in the color tuples of upper adjacent cells.
Yeah, so for instance, in this example here, if you look at the light blue arrows, when two edges in the same ring communicate, that's what these blue arrows show, the features of the cell they communicate through, the two cells, so the features of the ring they communicate through, that's also included in that message function. So implicitly through that, you get information from above.
Yeah, okay.
Let me move the slides back too. All right.
But yeah, it's also only happening because those messages, they include the co-boundary.
Yeah, so maybe for this particular, like for this ring transfer thing, probably adding co-boundary adjacencies also explicitly, maybe it would have helped, but we just didn't. Because it's in principle, like it should not be needed to add them separately as like just because of the proof.
Probably might help to get, you know, more robust results. Maybe in the training, in the optimization phase, maybe would help because we do have some noise, of course, here. So maybe it would help in that sense. But it's also reassuring to see that even if you don't include them explicitly, you're still able to solve the task. So it means that in practice, the network finds a way as we would have expected from theory.
And
so
yeah, we would still need L equals 3, right?
Yeah, I think so.
Yeah, in that case, let me think about it.
So it still needs to go from node to edge, from edge to edge, from edge to...
Yeah, it will still be 3.
Yeah.
Okay. Then let's get to real world.
Yeah, so this is a classic benchmark. So we experimented on it a little bit, although datasets here are very relatively small, at least compared to the ones we are now used to from OGB. So all methods basically suffer from very large standard deviation, and it's difficult to tell whether one method is strongly and significantly better than another. But still, we got pretty good results, especially on molecular datasets. So the one on the left, sorry. So I'm really happy to see we got basically the best average performance, and also on NCIE 109. We got also good results on IMDb and Reddit datasets, which are social datasets. So yeah, in principle, you know, rings might not tell you much, but the fact that rings of a certain size also do include triangles, this already gives you important information in social networks where triangles play an important role. So yeah, at the end of the day, rings turned out to be a good choice in general across the board. Yes, we have also some results on larger, probably also stabler or molecular benchmarks. So in particular, zinc and MolHIV. MolHIV is from the OGB, the OGB benchmarking effort, and zinc. Well, it's a dataset which is used commonly when for molecular modeling with GNNs. So we get very good results, I would say, with rings again, and this confirms the fact that rings are they convey a very important inductive bias when we do, of course, molecular modeling. So we experimented with 2 versions of the model. One, which is just without any necessarily having any constraint on the number of parameters, which is just CIN scene. And then we have scene small, in which we constrain the number of parameters to be in the order of 100,000. And we got pretty good results also like in basically all dataset versions. So in Zinc, whether we use edge features or we don't use them, we still get very good results. So for example, without edge features, even without edge features, we still have that the small network gets basically state-of-the-art results. On Zinc Full also we got pretty good results for both networks. Yes, and on Mol HIV, again, we managed to get very good results. It's interesting to mention here that on Mol HIV, we only used 2 layers. And this turned out to be enough. And somehow this gives us a further confirmation of the fact that in practice, you may be able to use a smaller number to make use of a smaller number of layers when you model molecules, and you potentially may have long-range interaction to capture. So there are 2 small bullets on the left, which I placed just to indicate the fact that HIMP and GSN, they are models which do include some form of information coming from rings. It's interesting to notice that these are amongst the most competitive models, at least in Zinc for sure. So it seems like this information is very important for this task. And we'll also verify this with a specific focused ablation study. So the idea was to see, to really single out the contribution of rings. So we basically trained another scene model without rings. And it's the same architecture, everything is the same, just we don't use rings at all. So they won't induce, for example, adjacencies between edges, for example. And they are not modeled at all. Of course, the performance drops with respect to the full model. And this confirms the fact that modeling rings is very important for this task. But at the same time, we noticed that the performance was not bad in general, and we actually got performance which was better than other standard GNNs. In order to, the way we explain this is the fact that still, even if we don't model rings explicitly, but still we model edges. What I was basically saying before, that is, edges are first-class citizens, so they are their representation is updated throughout the network, and at the end they contribute to the readout phase. In order to confirm this hypothesis, we also implement another method, which is what we call GNE custom. So we took the same scene no rings model, but we replaced basically our convolutional layers with convolutional layers in the form of GNE. Probably many of you are familiar with this, but it's basically a gene layer in which we also additionally include edge features. And again, we got a drop in performance. So this somehow, at least partially, confirmed our hypothesis that modeling and updating edges and using edges in the readout phase might also be important in general. I think with this, we end the presentation. Thanks very much for inviting us and for being here. And yeah, we're happy to take any other question.
Thanks for the awesome presentation. And I guess we have a question in the chat by Julia. Is CWL message passing capable of predicting capturing classical topological features such as the Betty number, or the Betty numbers, for example?
Yeah, that's a great question. Well, it depends in what sense. So obviously, like if you attach cells, for instance, exactly to the places that kind of correspond to like the topological features that correspond to the Betty numbers, you automatically can count them. So in that sort of trivial sense, yes, you can. It might be helpful. Something else that might be interesting here is that, for instance, if let's say you have a molecule, and if you attach these 2 cells to only some rings, then kind of the homology of the cell complex will become more interesting. just because you have this higher dimensional information. But then there's a question there if you can actually, if you do message passing on this, if you can actually do that. We touched a bit upon that in our previous paper on Weisfeiler and Lehman topological, where we looked at simplicial networks. We had some applications there that also use something called orientation equivariance that we didn't look at here. But when we use that on some tasks where these Betti numbers or like the homology of the complex was important, our network was kind of able to isolate the what's called the harmonic part of the signal. So that's part of the features that kind of correspond to these topological features like cycles and stuff like that. So it's kind of detecting the part of the signal that's kind of associated with the cycle or wrapped around the cycle. But we don't have so much theoretical work on that front. I have some potentially early theoretical results, but like not something like I can confidently show yet. So yeah, I'm not sure. I guess it's an open question theoretically. In practice, it seems to be able to do it to some degree at least.
Maybe there was some questions about the link operator. But maybe, yeah, sorry.
Yeah, but Kelly is raising his hand. Maybe we will go with that first.
All right. Thanks for the talk. That was awesome. I was just wondering if you guys had thought about doing or had some kind of like conception of what a pooling layer or like a coarsening layer would be, or some sort of notion of regularization as part of these cellular networks.
Horatio, maybe you want to answer?
Yeah, that's a great question. So we thought about it. We haven't explored this, honestly, a lot. So we had only a few ideas and a few thoughts. In general, I think one would be able to somehow adapt standard methods for pooling that has been proposed for GNNs. The thing is that a kind of pooling operation already happens behind the scenes because we have this hierarchy, right? So so when we read out at the level, for example, of rings or edges, like they capture some information coming from the lower part of the hierarchy, or if you want this posit structure, which completely determines the topology of the object. And yeah, we are basically summarizing some information coming from below. For example, it might summarize information for a group of nodes. So implicitly, this already happens behind the scenes. So probably like we might want to design a pooling layer which does something orthogonal to this, or which can complement this to some extent.
Because I also feel like a pooling layer may help with the long range signal passing, right? Like somehow, those two things seem related in my head.
Yeah, I guess you can have some maybe like these virtual nodes people have been trying in molecules. Maybe you could think of that as some sort, like maybe analogous in some sense to what we're doing. As Fabrizio was saying, I kind of like to think as these, well, if you look at this diagram here, it's kind of some sort of vertical pooling that's happening, and it's kind of happening at each layer rather than, kind of always coarsening your representation over time. And this seems to
you think of the two cell as a pooling in some sense, right? Or
yeah, because it kind of aggregates all the information.
The two cell you can kind of pass through you're kind of pooling everything in its boundary together.
Yeah, exactly. Yeah. And this seems to work. I think there's been some evidence that these coarsening layers are not so useful in graph neural networks so far. So usually if you just do some readout and keep all the information, that does better in general from what I've seen. And maybe this might be a good compromise, like the fact you do this kind of vertical pooling at each step, you don't lose anything because that kind of moves over to the next layer.
So you almost think of like the two cells as a pooling layer for GNNs in some sense already, like.
Yeah, I think one may think of this way to an extent. Of course, there's not a one-to-one mapping, probably, as Chris was saying, like this happens every time at each layer. So, but this might also be a feature, like the fact that at each layer we still keep the complete set of nodes, but at the same time we do pooling as well. So might be a good compromise. If you want to maybe single out something that might be the counterpart of pooling, is I would say it's definitely this MB message here, because it's basically we get something from the boundary and we aggregate it. So I guess MB, the message MB here is definitely a form of pooling, which is happening behind the scenes.
I also had one other question, and it's that in, normal topology, like these cell complexes, the cells have an orientation, right, normally. I suppose when you're working with regular CW complexes, you can think about the post set just as like the partially order of the faces and get a lot of that stuff back. But I was wondering if you'd come up with seen applications where the orientation of the cells is important.
Not yet. Like, so in the previous paper on simplicial networks, we look a bit on that. So there was like edge flow signals, and there's been like other great papers on that. Like, I think they looked mostly at edge signals so far. That seems to be like at least one application people clearly identify so far, but there hasn't been so much beyond that. I think there's definitely going to be some applications for physics there, but more like from like a mesh perspective. Like, if you have some surface and you have some integrals, so the signal associated with the edges is the result of some integration process, and then again, the result of like the features of the two cells or triangles, let's say if it's a simplicial complex, is the result of some integration, because they integrate a surface or an edge that automatically depends on an orientation, because integration depends in which way you take the integral. So
yeah, for sure.
So something like that.
More along the physics line, probably.
Yeah, like simulations, that kind of thing.
Yeah. All right. Thanks again for the talk. That was really helpful.
Yeah. Thank you for your questions. Were very good.
Yeah, like maybe for the pooling, we could do the readouts separately for like phases, bonds, and atoms, or we could maybe, like you mentioned, having a global, like a virtual node, and maybe just having those between the phases.
Yeah. So something that's directly compatible from the current GNN literature is top K pooling. So you can do top K over nodes, and then you keep all the stuff above that survived the pooling. So like, if a node disappeared and that node was involved in some two cells, for instance, then obviously you're going to disregard that two cell because you don't have it anymore. So something like that could be done.
Is it a limitation that you can only pool things that lie on a ring? Or is that like actually something that is like part of, because I suppose you could also do like these virtual nodes between structures that don't have like a circular boundary, right?
Yeah.
If you think of it as a pooling layer, then yeah, I guess what is the intuition behind forcing things to be the boundary of a high dimensional cell to be pooled?
Yeah, so I think that's related to like the regularity of the cell complex, basically. So if you want to make it regular, then you kind of need to attach these at least two cells, the simple cycles and so on. You need to attach things nicely. But if you attach things more in an ugly way, you have more flexible structures. And that's something we kind of discussed, like well, not in the paper, but like among ourselves, like how important is regularity and stuff like that. We don't have yet like a very good answer. Something that it's definitely like related to this is like all these sheaf stuff that we've mentioned maybe in the appendix. I don't know if you managed to have a look, but there's like some sheaf convolutions that you can associate with the cell complex. All these message passing can be understood as generalized convolutions, as with normal graph neural networks, where you have these what's called a sheaf Laplacian, and again you need orientations for that. But yeah, you get that. But for the sheaf Laplacian to be defined and all that stuff, and all that spectral theory kind of relies on regularity. So at least for that connection to be made, and maybe borrow some of the spectral approaches or the more interesting stuff on that side.
Like Jacob Hansen and those kind of
yeah,
things?
yeah,
Okay.
yeah, exactly.
And that's in the appendix of the paper at the start.
Yeah, yeah.
Okay, awesome. I'll have a look
Yeah.
at that for
So
sure.
that definitely has, it's the regularity is definitely required for that. But like if you don't care about that kind of stuff, you can probably relax also our results if you don't make the glowing extremely weird or something.
Yeah,
so
I was definitely imagining regular CW complexes, because like the combinatorics of like how you even define what gets the message passed where would just be
yeah, exactly.
But yeah, thanks again. Sorry for extra questions.
All right, thank you.
Okay, then Christian, Fabrizio, how much more time do you have?
I'm free to stay around.
Okay.
We have to run in a few minutes. So maybe last question for me, maybe. Yeah.
Okay, then let's maybe go with the one we've had in the chat for a while now. When you mentioned the boundary, do you mean the link operator? The link operator is an operation of simplicial complexes related with the boundary of the star operation of a simplex. You know what's meant?
Yeah, I need to remember exactly the definition of the link. There's definitely different notions of neighborhood. So like, for instance, there's like as the star operator that has been mentioned. So you could think of other notions of neighborhoods. I remember checking at some point these kind of things, and kind of you eventually get the same kind of information. It's just that it might take more steps just because you look like literally like in your immediate neighborhood. So like, for instance, you don't consider all the stuff above you. So like, for instance, a node does not talk directly, like if we talk about stars and stuff like that, like a node doesn't talk directly to the cell it's part of, but it doesn't need to, because it eventually that information will reach it in 2 steps or something. So I think it's slightly different. But like, I think in general, it's you aggregate the same kind of information eventually.
We wanted to keep it basically as close as possible, as intuitively as what we already have for GNNs. And so the idea is, let's first define an update rule which works as locally as possible, and then of course we just stack all these layers, and the information will propagate anyway. So that's why we started with this idea instead of considering other possible approaches. I think the bit sigma you mentioned on the aggregation is related with the link. Okay. We'll take a look. I think it might be interesting to investigate this further. Thank you for the pointer.
And then Fabrizio, while you're still here, like you also had this paper on subgraph isomorphism counting, where I think you also looked at some substructures like 6 cycles, for example.
Yeah.
And yeah, I mean, we could also look at, I don't know, counting 10 cycles and so on. And if we have a SYN that goes to cycle size 10, and if we have subgraph isomorphism counting with cycles up to 10, how do those compare?
Well, so in practice, the architecture is very different. Like in GSN, you always do message passing at the level of nodes, and basically what you get from counting these substructures is you are able to break more symmetries between your neighbors, and this is why you get more expressive power in GSN. But still, like, the message passing is performed at the level of nodes. Whereas in SYN, as we already explained, basically we have this whole hierarchy, and we keep updating, for example, the representation of edges and rings and so on, and they do induce adjacencies. So rings are induced, and edges they all induce adjacencies. Whereas in GSN, we only basically work at the level of what we call in SYN the skeleton of the graph skeleton. Yes. In terms of expressive power, it's harder to say, I guess. Probably in the case of an upper, like if K is upper bounded and we only consider rings, probably we might be able to say something more specific. But the thing is, both GSN and SIN, so they both kind of cut through the double hierarchy. So it's not that easy to really quantify very precisely what's the expressive power. At least it's not easy with the language we have at the moment, which is the one of the KWL test. So, but I mean, I think we believe that's actually okay, and probably in some cases it's actually better. And in GSN, for example, we have a nice ablation study where on zinc we kind of considered other substructures, so not necessarily rings, for example, like say paths or trees, and the idea is that so in principle they are able to break the symmetries between nodes even farther. So when we use this information on top of nodes, you have an entropy at the level of the node descriptors, which is basically even smaller. Anyway, so basically the descriptors are tend to be more unique. So in principle, you would think that you get more expressive power, and this is good. But what happens at the end of the day is that this kind of model is not able to generalize because it generalizes much worse than when using rings, even though maybe rings do not induce such a basically uniqueness at the level of the node identifiers. Sorry, I think it was a higher entropy. Yes.
Okay, but I mean, I get the difference. With SIN, we have like long range interactions, for example, that we don't have with GSN.
Yes, exactly. This is because of what I was saying before, that even though you kind of capture this information, still this doesn't induce adjacencies. So this wouldn't modify the way or have an impact on the way you exchange information, whereas this happens in SIN, basically.
I guess
another possible difference here is something that we didn't have space to mention in the paper anymore, but it's related to the anisotropy of the filter. So you could think of in SIN, you kind of like if you have, let's say, I don't know, maybe two nodes communicating, and that message eventually kind of gets modulated by the presence of a ring. So you can kind of talk differently to different neighbors if those neighbors are kind of part of different rings. So you also get that information. So you might modulate it in an interesting way just because you have the features of the ring that kind of eventually get propagated to the feature of the edges between them. So then you kind of, when you talk to another node, you know, oh yeah, it's this ring, or no, it's this other ring that's, you know, maybe it's not important for solubility or stuff like that. So that might also help. Whereas in GSM with the features, I guess you kind of get that to some degree, but maybe your neighborhoods might still look very similar, even though, you know, you consider it in terms of counts of, yeah, just this kind of more advanced features. They might still kind of not be able to make it so anisotropic in some cases. And I guess this is also related to long-range interaction. The fact that, for instance, you are able to distinguish these two kinds of rings is because you talked to some other node on the other side, and then, or you have all the information about all the other stuff in the ring, in the features of the ring, and then you're ready to modulate any sort of smaller communication at the local level between nodes. So in some sense, it's some sort of higher order structure-driven anisotropy filtering that might help in practice.
Okay, but to the point when we were talking about the sort of how messages propagate, that's actually also different in SIN, and we don't just have theoretical higher ability to distinguish non-isomorphic graphs. There we have the problem SIN has oversmoothing problems. So like the relation of SIN to oversmoothing.
We haven't studied it.
I just wanted to say I really have to run, and I just wanted to thank everybody for being here, and thank you, Hannes, for organizing this. Sorry for the
Then
interruption.
I want to say in the name of everyone here, I guess, and the people who already had to leave, thank you very much. And yeah, have a great day.
Thank you. Bye.
Yeah.
Bye.
Yeah, on oversmoothing, I think there are some questions still lurking, like we don't know, like also because generally the results about oversmoothing kind of tell, say the theoretical ones, I mean, kind of say, okay, all the signals in the same connected component kind of converge to the same signal. So you have like a constant signal in each connected component. And that seems to be related to the harmonicity, like the harmonic components of the nodes, basically. That basically corresponds to constant signal on each connected component. And then what happens if you have features over edges, then your harmonic signal will correspond to these cycles you might have. So then there's an interesting thing, like, if you get over smoothing there, is it going to behave the same way? Like, as in, is it going to be associated with the harmonic part of the signal in that space, like in the edge space? So that basically means you're going to be associated with the cycles this time, not the connected components, and so on. So if that happens, maybe it's not that bad, because if you have lots of cycles or something, it's not a boring signal. That's what I'm trying to say. So even if you oversmooth there, maybe you oversmooth in an interesting way. But I have no idea. Like, I'm working on some things in that direction, but I don't have results there yet either.
Okay, yeah, but then let me make some advertisements here. We will be talking all about oversmoothing on the 19th of October, where we have Yuri Alon with the bottleneck of graph neural network and its practical implications paper. Yeah, but about our paper right here, any other questions before I go ahead? Then, yeah, did you also try like different message passing schemes where you, I don't know, for example, also look at lower adjacencies and just test it on some data sets?
We tried it all in once. So that was in the early beginnings for the previous paper. We started with like complete set of adjacencies in the beginning, because why not? And then our machine literally exploded. So one problem with lower adjacencies, and that's what I kind of alluded to when we were on that slide, there's some benefits to that pruning. So with lower adjacencies, you can show that even if your graph is extremely sparse, your lower adjacencies between edges can be super dense. And the classic example here is when you have a bunch of edges forming like a star. So you have like a star graph. If you think about the line graph adjacencies in the star graph, you get like a complete graph in the edge space. So then you get something extremely dense. So that's a problem. And even for real world graphs, that will kind of explode in your face. So that's where we kind of stopped doing things. Another combination that is computationally efficient is just boundary and co-boundary. So some sort of just vertically in some sense, but you still propagate kind of information sideways, but it's just slower. So if you imagine like, let's say, so like two nodes communicate with the edge between them, but at the next step, then one of the nodes will extract information from that edge, so automatically it can implicitly communicates with the other node. So you do transfer information horizontally as well with that message passing, but it's just slower. We haven't tried it, but it might be important for some topological applications, just because those message passing procedures are inspired from like these boundary and co-boundary operators from topology, essentially, or geometry. But we haven't tried that either. One reason we haven't tried it was that this kind of horizontal element was so important in GNNs so far, and kind of made them work, that we were kind of skeptical about removing it. So we haven't. Or one option might be to keep it and also include co-boundaries, which we discussed earlier. So that might also be an option, but again, we haven't tried. There's literally a lot to do on the experimental side, like even in terms of what aggregators we use. Like there's been some great research also in our group with like PNA, with the PNA architecture, and they actually are very suitable for some problems we had. Like, if you use the same kind of weights for, like a 10 ring and a 4 ring, they obviously get messages of different magnitudes after you add them up. So that might be a problem with just summing. So doing something more fancy like the logarithm stuff they have in there or stuff like that. It's kind of it's probably something that would improve, but we just haven't tried. So probably these results can be pushed quite a bit, like with more stuff like attention and so on. We literally haven't. We just basically adapted SIN, well, SIN to be this SIN. Yeah.
From sin to sin. Okay, that's progress. But so for example, if we have a huge ring and we have our face and that's aggregating from all of the bonds, then yeah, we have a huge range of sizes that our faces can take, and then it might be nice to have some sort of scaling that scales after we take some sum, it scales it back to something. But I guess if we take the mean, then
yeah. Another problem with GIN is that for our specific application is that you end up with kind of very different possibly different magnitudes of the features at each dimension. So specifically on rings, like in general, they will be higher magnitudes than the features on nodes from what we observed, or at least different kind of statistics. And then, for instance, that kind of doesn't allow you to reuse the same weights at all dimensions. That seem to break, or it doesn't work very well. So you implicitly have to use more weights because of that. You need to use like another set of weights for each dimension, another batch norm in each dimension. So that again, like if you use some smarter aggregators, that might alleviate or fix this problem.
Okay, but then can we go back to the message passing slide?
Sure, yeah. One sec.
Because like inspired from your CWL test, what I would have done is to just have this U function here, or like, to just take the U and it aggregates, or we have U of aggregation of, and then we have the upper adjacencies and the boundary, right? Because
so do you mean you would aggregate them together?
Yes, like when I create, when I'm at a face or at a bond or at a node, then I look at all the features of my upper adjacencies and of my boundary and aggregate those. And then we have sort of this WL test, or the CWL test, without the two unnecessary aggregations, so to say.
So the reason we haven't done that was like just to keep things as general as possible. So these formulation, because you don't aggregate things together, you're kind of allowed to use separate weights for each type of adjacency. And also it's not equivalent unless you kind of have, from a color refinement perspective, I mean, unless you have different colors for things of different dimensions at initialization. So if you have that, obviously you can distinguish things no matter how, if you group them together, since they have different colors, like non-overlapping ones, you will always be able to distinguish them, and you can aggregate them together and put them in the same bag. It doesn't, it doesn't really matter. Yeah, so, but that's more like a technicalities. So I think that's mainly the main reason, just to use different weights. This thing still doesn't stop from, so like this formulation here doesn't stop you from doing what you suggested. Like the U update function could still kind of take these two messages and take their average or something, and the message could be just a sum, or and then that kind of makes it like what you suggested.
Yeah. Okay, but I mean, we're still here looking at the co-boundary. If we're creating the message for, if we're creating the message for our current sigma that we're looking at, we have the information from the co-boundary in there. And on page 4, you say, additionally, in virtue of theorem 7, we consider only the boundary and upper adjacencies between these cells. Yeah.
Right. Okay. So I guess it's because like we haven't really defined this very precisely in the presentation. So by upper adjacencies, what we mean is basically this third multiset here. So this one, right? So that's what we kind of name upper adjacencies, and this is what we name co-boundary adjacencies, just because this two cell is on the co-boundary, well, of this yellow edge. But what we've done, like here, just to keep this as general as possible, we essentially included the features. So like for instance, let's look maybe at the concrete example here. So let's take this green edge, right? So these two communicate here, right?
Yeah.
But when these communicate, like the feature of this thing are also included here in this communication. So information about co-boundaries is still included in some form in the upper adjacencies. So what we mean by that sentence there is that we simply don't use this, and we don't use these ones. But this information for here is still present here, but in another form. But what the theorem kind of shows is that, like, from this encoding, no matter how the cell complex kind of looks, you're still able to reconstruct this multiset here. Obviously, this is a very simple example because it's a single two cell. It can be much more complicated. But like essentially what the theorem is saying, this part here, you can rebuild this second multiset from that one. So that's why you don't need it. You can remove it. Obviously, so that's just color refinement. But obviously, in practice, that affects the flow of information and you know how the information kind of flows and how you parameterize things and so on. So in practice, it might help you to have this thing. It's just that we haven't tried.
Well, we kind of do have it, right? If we include it in the message that we generate for our upper adjacencies, then we do have it.
Yes, you still have it, but you don't want to remove this thing from here because it's having it there. It's actually quite powerful. So this allows you to have the anisotropy I mentioned. Or like what's commonly done, like for instance in the original paper from Gilmer, again, which was kind of focused on chemistry and so on. These edge features are very important there to kind of modulate the interactions between atoms, and you also usually have features about the bonds. So it's very important to include these features there. So that's why we kind of went with the most general thing possible. And something else that I would say here, that even though it's not really about these colors being present in both ways, but it's more about like actually being able to reconstruct the second multiset from the third multiset, which here seems obvious, but like you could have more general things where maybe it's not that obvious. But this is more like the easier part of the theorem, let's say. I think more complicated is about removing these things.
Yeah, but still, if we imagine these colors as just features, then in the end, we have the features included in all of the information that is going into the update of our node or our edge or our face.
Yeah.
So yeah, I was just confused by this, that we only consider the boundary and the upper adjacencies, and then in the message passing we still have the co-boundary.
Yeah, I agree. It can be a bit confusing, but that's what we basically mean. We disregard them as a separate thing here in the second entry.
Yeah. Okay, so you would say that you do include the co-boundary if you have it as an additional message.
Yeah.
Okay. But then, like you also mentioned this, the long range interactions, and then you mentioned if we have different, what's it called, functional groups in a molecule. And yeah, that has me thinking like this notion of a global virtual phase, or a global virtual phase, like in GIN with a virtual node, we have this virtual global node, yeah, that just aggregates from each node in every layer. What if we here have a virtual phase that aggregates from every phase in each layer, and then we could have like communication between the different functional groups if they contain a cycle?
Yeah, I guess so. I think that would kind of classify like as a non-skeleton preserving transformation. Where was that? Yeah, I was on the next. Yeah, so like there you kind of, I guess to add the new face, you also have to add new vertices and new edges, probably, or in general, if you add other kinds of structures that are not based on what you currently have already, then I guess our results don't directly apply. I'm not saying it wouldn't be useful. It's just that it's something kind of we purposefully ignored in the paper. But yeah, I don't know, like if there would be a difference between that and just adding like some sort of virtual node or something like that. I guess what you, to have something more closely, I guess that kind of becomes a hypergraph. So then you can have, it's more like a hyperedge or something like that. If you have something along those lines, just because you can't connect things arbitrarily. So you would need something more flexible. So you would need like a hyperedge, and then you could include whatever you want in that hyperedge. But then things also get messier, as I was saying. So that's even messier than non-regular cell complexes, just because, well, yeah, it's a mess in hypergraph space in terms of spectral properties and so on.
Yeah.
You get much more complicated things. Yeah.
Sure, maybe we don't no longer have some nice spectral properties, but just intuitively, I mean, if we pass the information between all of the rings, sounds like something I would want to try.
Yeah, I mean, definitely, like it's something that could help in practice. I think with these things, now that we discover multiple spaces, like we have simplicial complexes that we studied in a previous paper and other people started looking at, and cell complexes, and then we kind of have hypergraphs as the most general things. So I kind of see them as this hierarchy with cell complexes in the middle. And I think a key part in applications will be kind of to identify the right level of flexibility for your problem. And that will kind of, if you don't need more, don't use more, basically. So I think that's been the case with these molecules, where they fit very well with the cell complex structure, like edges, nodes, and rings. They are normally considered as sort of first-class citizens by chemists, because you have atoms, bonds, and rings, and they kind of think of molecules in terms of these structures. So it was a very natural mapping from the mathematical abstraction to something we really care about in the real world. Obviously, for some things, as you mentioned, you might want to do some more complicated things, and maybe these kind of strong link breaks, and then you need to consider a more general abstraction. But you also lose something with that, but you also gain something. You gain more flexibility, but maybe you lose your ability to analyze certain things and prove certain things as well. So it's about trade-offs, basically.
Okay, and something else I was thinking, because you assign these features to the faces in the beginning, and there you, for example, do something like averaging or taking the sum, I think, of all of the node features, right, to get the initial features for a face.
Yeah.
Is that correct? Yeah. Okay. And what about maybe if we having a different phase feature depending on whether we just have a usual 6 cycle or we have a 6 cycle that is I think benzene ring, it's called, where you always have double bonds in the 6 cycle.
Yeah, you can definitely do that kind of thing. And initializing these higher dimensional cells is probably something that deserves further attention. And we haven't really bothered that much with that. We just tried mean averaging of the ring or node features, and or both of them, or summing, but we haven't tried much beyond that. And probably there's more that can be done, even parameterizing the initialization. So essentially having some parameters associated with, like as in with the further pooling, like in the boundary messaging. So you could kind of do like one round of boundary messages in the beginning to kind of populate everything, and then you do the normal layers. So that could also be an option, just to have it parameterized, like to learn the way to initialize.
Would it be a stupid idea to, for example, also include the size of the ring in the initial feature of the face?
No, I mean, that definitely would be something worth trying. I guess, I think in PNA they do something like that. I think the size of the degree of the node or something, or other approaches definitely do that, like they include the degree of the node in the message passing to kind of modulate the aggregation in some sense. So that could definitely be done here as well. It's kind of equivalent to that essentially, because your boundary size is kind of the neighborhood size for that adjacency, basically.
Yeah, okay. Then
I see there's also some question on the chat.
Yeah. The region of sin is greater, less than, or equal to the linear region of sin. So with CIN, because in simplicial message passing we analyze these linear regions.
Yeah, I see Muhammad says thank you for sin and sin. Yeah, we definitely caused some confusion there. Yeah, so in the previous paper, maybe just for some context, we did some linear regions analyses and showed, like, we placed some upper bounds for simplicial networks. So these work on simplicial complexes, which are a particular type of cell complex. So that's just the background. And we've done some analysis on the number of linear regions of these models. Essentially, the same kind of, I think the same analysis should also apply here, just because our proofs previously were kind of general, and we assume like some are relatively flexible matrices involved there. And here, what's only changing is kind of the structure of the boundary matrices. Like, you can have things linked in more complicated ways, but fundamentally the bounds probably remain the same as far as we thought about it. We haven't done it in detail, but I think the same theorems should probably apply relatively trivially for the latest paper. Now, I'm not sure exactly about the linear regions between SIN and SIN. I think, yeah, it probably, so the only change is the boundary matrices that now have different structures, so they might have different ranks or something, or that might slightly change them. I would say they're roughly the same probably, but yeah, I don't know, to be honest. But yeah, that's the only change. So there are just some changes in these matrices and what their allowed shape is. And I'm not sure exactly in the theorem how much we took this constraint into consideration when computing the upper bound. So we might have the same exact bounds. Yeah.
Well, okay, but you also mentioned this importance of the edges for these molecular tasks, and cool by Muhammad, I have to agree, mentioned the importance of edges for the molecular tasks, for example, and these message passing neural networks always looking at the edge information each step. But in message passing neural networks, or like the work of Gilmer in 2017 at least, we don't have edges that are being updated. So do you know any work on that? Like, what's the importance of updating edges or not updating edges? And I think you also had these experiments where you looked at.
Yeah, So I think that something edge features are kind of highly undervalued in the community, in my opinion. And I think that's also partially because we see edges just like some, something that's kind of there in the message passing, but we don't really care about it a lot. It's more like, oh yeah, we can put it in the nodes or whatever. But as soon as and that might also because, we haven't found interesting things to do with them because there was no higher order structure there. So, there wasn't something very interesting you could have done with them, I guess, if you just have this normal graph. But like if you process them in the right ways, I think it can definitely help. And I think that's also in our results. Maybe let me go to that slide. I think it was kind of interesting, something in relationship with GSN. So on zinc, because we had that ablation there. So if you look on zinc at sin small, without edge features, it has the exact same performance as GSN. But if you look at sin small against GSN with edge features, you get like, 10 more than 14 extra points there. And that's only because, of the edge features. And this sin small model is also about 5 times smaller than the GSN here. So I think GSN here has 500K parameters. Sin small is like about 100K. So it seems like it's making better use of the features just because it's processing them. But I think it's not just about processing them in general, but like how do you process them and what do you do with them? Yes. So in this task, like apparently having those rings and having the upper adjacencies and so on, seems to emulate the inductive biases of, like whatever chemistry does here. But yeah, maybe for other tasks, that's not great. But that's why I think it's undervalued, just because everything that's been tried with edge features has been kind of boring. Once you start to treat edges as more like first-class citizens and not special in any way from, compared to the nodes, for instance, then maybe you can do something more interesting with them. It's something I've discussed at some point also with a group member. And yeah, we were thinking at some point to actually make some benchmark or something and benchmark all these methods doing different things with edges just to kind of figure out, okay, what's the deal with edge features, but we didn't have time to do that eventually. But yeah, I think it's an open problem and what's the best way to do with them. But yeah, I think we can do more with edges in general.
Do you know any work on that, like comparing networks that have edge representations that are being updated with the ones that don't have edge?
Yeah, I don't know. I've seen a paper, I can't remember the name. I think it was on Open Review. I think they were considering random edge features. So adding some randomization during training, and that seems to have helped somehow. And other things like that. I think there are not so many papers. I know I asked on my group Slack at some point. I think it was in relationship to our previous paper, just to see if there's anyone doing something with edges. And I think I got 2 papers people knew about, but I don't think they were doing something super interesting. But yeah, I don't know. At least I don't know of any like sort of state-of-the-art method doing something very complex with edges or.
Yeah. Okay, then while we're at the slide here, hey Christian, may I ask whether the model suffers from overfitting? I think mole HIV is very easy to be overfitted by Ling Xiao Zhao.
Yeah, thanks for your question. So I'm not sure. So I think for mole HIV, we want to do more experiments. So we recently added it to the OGB leaderboard. And we noticed that everything that was ahead kind of had like 10x more parameters at least. So, and I was talking to Fabrizio about this, and I think we mainly try smaller models just to kind of train it in time for the deadline and, have time to actually train it. And I'd be interesting to see what happens once, we try a bigger model. Does it actually overfit or something? So yeah, I'm not sure. So like the model we report here has like about 250K parameters or something like that, I think. Yeah, so I don't know. And the smaller one has like one in the order of 100. and there seems to be like an improvement from 100K to 250K, but probably we're still not quite in the overfitting regime there. So, I don't know how much this can be pushed further without actually results decreasing or something. Yeah, I think we're going to do that and probably add it to the final version once it's accepted, hopefully, or yeah, just some future version.
Yeah, I think the only non-fingerprint methods before you right now is we also had the Graph-Former paper in the reading group once, and that's the one before you. And yeah, they have 47 million parameters compared to your 200,000.
So I think that's a version of Graph-Formers that also uses neural fingerprints. So I think the one without neural fingerprints has less than us right now. But yeah, and also I think the Graph-Former uses, I think 100x more parameters than us on mol HIV. So it doesn't seem to overfit there. On the other hand, like I've seen Graph-Former doing very good on PCBA, where we didn't have so much time to actually try our model, and that's also something else we want to try there. So yeah, I think from initial results there, the model was not doing so well, but there was more like 2 days of trying some things before the deadline. So
yeah.
we didn't have much time after that because we all took a break after New Year's and everything.
Yeah.
So yeah, we'll have to try to see. It's a much bigger benchmark as well, so it takes much longer to train and stuff.
But if you already tried mol HIV, why don't you try all the mol PCBA? Okay, that's maybe a much bigger data set that takes a bit longer, but all of these super small data sets with the, I don't know, mol base, mol BBBP, mol ESOL, yeah, those run in a few minutes. And I think a network like yours that's that doesn't completely overfit on these types of data sets, maybe it's super good there.
Yeah, we should definitely try. I think the problem with that is that they don't have a leaderboard, so it's a bit harder to I think the smaller molecular ones. So it's a bit harder to kind of assess, if you get a number, how good it is and that kind of thing. So you kind of have to run your own baselines, which is not like horrible, but yeah, it takes some time basically.
Yeah, but you can still compare with the other papers that use the OGB datasets. I mean, it's the same data split, right?
Yeah.
Okay, but then I will wait a few seconds for any other questions. And otherwise, I would ask my very last, very mean question, like, may I ask for the slides? Yes, we will probably upload them on the website if I may do so. Yes.
Yeah, we will definitely send them over.
Yeah. And the last mean question I wanted to ask is, do you have any regrets about getting everything so mathematical with the simplicial complexes and then the CW complexes, while in the end what we have is that we just add a new instance or a new feature that's being updated for rings?
Yeah, I mean, it was definitely a discovery process. I think it would have been much harder to get to something like this via other routes, even though it's, it seems very kind of maybe obvious in hindsight that, okay, let's use these bigger things in message passing. But I think it would have been harder to get here and also kind of to understand different trade-offs, Also, the theory helped us quite a bit to kind of choose the right message passing on these things. Otherwise, it would have been something like completely empirical. And I still think, like for me, something is more important if it has more connections to more things. And at least maybe it's kind of like just because I love mathematics, so something, more deeply rooted and with more relationships to other things, it's kind of more important. So I think the fact that there are so many connections with differential geometry, algebraic topology behind these things, I think there's definitely more stuff to be done, and we're kind of in a process of figuring out applications and what's the best thing to do. There's also like meshes, simulations, that kind of things that we haven't looked at yet. And again, like all the meshes or surfaces, you can triangulate them. You have a simplicial complex. What do you do there? And like if you have a flow on a surface, you want to discretize it. Again, you kind of have information on the edges and so on. So yeah, I think I don't personally regret it. I think, and in the end, we also ended up with something that actually works with this latest paper, at least in these benchmarks people care about. Not that the previous paper doesn't work, but probably it's a more obscure, let's say, use case from what we've seen, like with these, edge flows and something like that is not something people looked at a lot yet. Not that it's not important. So yeah, I really don't have regrets. I think from here it's easy to kind of extend this and just do some arbitrary hierarchical message passing of this kind now, and maybe it does slightly better or something. Maybe it doesn't. I don't know. But yeah, I don't personally.
Yeah, I hope not. I mean, also from my the simplicial message passing paper, that was like one of my favorite papers, or like just in general this line of work, for example, where you also look at the substructure, subgraph isomorphism counting, and then simplicial message passing, and now you do have this cool stuff like in simplicial message passing, but it actually is super good for practical tasks. So yeah, that's awesome.
Yeah,
but
thanks. Great, happy you liked it.
Yeah, you were saying easy to extend it. Muhammad Anwar is saying, what is future work?
What's future work? So I'm not sure yet. Like we still have to see. I'll also be starting my internship at Twitter in a few weeks, so we'll see like what we end up working there as well with Fabrizio and others. So yeah, but I think it's still definitely going to be topology. I think the bigger theme here is to kind of, like I think, as I said, like graphs are not enough in general, and you want to have either graphs with some fancy stuff on top or some different kind of space altogether, and see how these things can help us solve some problems, but also understand. I think that also makes us understand how the absence of those extra features, extra mathematical tools on these objects kind of make us, perform worse in graph neural networks in general. So yeah, I think that's kind of the bigger theme I'm going on.
Okay, and like one thing I wanted to ask, do you like if we're looking at bigger graphs, then this message passing could get a bit more computationally expensive, right? And like, do you think this could also find applications at some point for some node classification tasks, like run it on sites here or something like that?
Yeah, I mean, for small, well, yeah, it depends. Indeed, there are some problems if you don't make assumptions, and those assumptions hold here for these molecular problems. So for instance, the molecular graphs are pretty much always planar, topologically planar, unless there's some very weird, I don't know, lab molecule or something like that that people artificially created. So that gives you some better guarantees about things in general, and everything's nice. So yeah, I don't know. I think maybe one setting where graphs can be huge and these can still be efficient are, as I said, any sort of mesh or something like that, just because everything's kind of nice there and nothing explodes. You just have a surface and it's discretized essentially. So that could be a place where you can actually use all types of adjacencies as well without problem. So yeah.
Okay, so basically anything that's still planar. This way.
Yeah, I think for large graphs, maybe something that's possible is, well, triangles are easy to find, or you can find them pretty fast in general graphs. So I think it's number of edges to power 3/2 complexity. And you can also find quadrangles in, I think, maybe, I don't know what was the, oh no, it's, I think it only in planar graphs, you can list them in n² or something, in general planar graphs. So yeah, I don't know, like maybe if you have some algorithm to find some specific structures fast, probably that would be the way to go. But yeah, I think you kind of depend on some assumptions with this family of methods. So yeah, it's more like a matter of finding some problem that matches these assumptions, I think.
Okay. And yeah, we also, okay, one, I mean, I think I said a few times now, last question or something like that, but just about real quick, the cycles, I didn't understand that you talk about induced and simple cycles. What's the difference?
Right, so basically in like just some general cycle, you can have this kind of chords. So an induced cycle is basically one where you don't have chords. So you don't have other connections between any nodes in the cycle. We haven't tried a non-induced cycle, so we haven't tried general cycles for the lifting in practice. Also because I think generally they are more, yeah. So yeah, like they could be much more. So we haven't tried. Also because like rings are kind of induced, like the chemical rings. So yeah, it's not something we tried.
Yeah, so if you go to the slide where you show the two graphs that cannot be distinguished by the WL test. Yeah. Then on the left, the two, we have two induced cycles and we have three simple cycles, right?
Yeah, exactly.
Okay.
Yeah, but something that does happen with induced cycles that helps us kind of having these kind of, I think they're called breached compounds. So like imagine if these two rings are separated by two edges rather than one here,
yeah,
then the bigger thing is an induced cycle because the node in the middle is kind of not part of right. If you take the induced subgraph formed only by the nodes on the boundary, it doesn't include the node in the middle. So then technically it's an induced cycle. So it has some sort of longer chords there.
Yeah.
So then you kind of get there three induced cycles, I think. And that kind of is a very easy way to kind of, in our model, to then detect breach compounds, just because they are in some very particular types of adjacency between each other. They have many overlapping edges and so on. So, well, I don't have a proof or something, but like intuitively, that should quite easily, you know, detect these sort of compounds.
Okay, then that would be it from my side. Other questions? Muhammad sent a nice paper on efficient enumeration of cordless cycles.
Oh, thanks for that. Yeah, I'll definitely check it out.
Okay, good. But then I will make my advertisement round about next week, where we'll have Georgos Bouritsas and Dr. Andreas Lukas from ETHL, about their paper on learning how to compress graphs. And it's also by Michael Bronstein, who was also author of this paper. Good, but then back to this paper, and because I mean it's just it's a nice thing we have in the end, this SIN that works super well, and it has so much rich theoretical work behind it. So thank you for the awesome paper.
Yeah, thanks a lot for having us. It was definitely a very interesting discussion.
Okay, then I guess let's call it a day for today. 2 hours of your time, Christian. Thank you so much.
Thank you, everyone.